Hello, in today's video we're going to be talking about the heat equation. And we started to talk about heat in its infancy on Monday when we talked about the energy of the system. And we came up with this very simple equation that related the energy of the system to two different variables. The first one was work, and the second one was this term of heat. Now we didn't have an equation on Monday that identified what heat was. We just started talking about this understanding of heat. But we did say on Monday that the work done either on the system or to the system, we're going to neglect. So in this case, the energy of the system is going to be directly related to the heat absorbed by the system or the heat given off by the system. We're not going to identify, or we're not going to work with this work term until next semester. So we don't even have to worry about that. So our new equation is just the energy of the system is going to be directly related to the heat that either the system absorbed or gave off to the surroundings. So we have a very simple equation that we can identify what heat is. It relates the mass of the substance, the temperature difference of the substance, either it gave off heat or it lowered its temperature, or we added more heat to it and it raised its temperature, and something known as the specific heat capacity or the molar heat capacity. Both of those are constants, and they're found in a table in your textbook. I will give them to you on your exams or quizzes. You can always look at I think it's page 238 in your textbook. So we'll talk about those two constants. But we're going to now write out the equation that relates Q to those very simple terms, the mass of the substance and the temperature difference of this substance. So heat is equal to the mass of the substance times this new unit, this new constant of specific heat. Now this is where it gets tricky. So next, in the next chapter, this lowercase c is also going to be used for the speed of light. But for the thermodynamics section that we're in right now, lowercase c stands for specific heat capacity. Okay. And then we're going to multiply that by the change in temperature. Now remember, change in temperature, this delta, means temperature final minus temperature initial. That is all that's required in order to identify what heat was either absorbed or given off by the system. It relates the mass of the substance, the specific heat capacity of the substance, this is unique to the substance that we're looking at, times the change in the temperature. So I have a little mnemonic that I like to use for this one. Those of you who are medical or pre-med, you're going to end up taking the MCAT at some point. The right-hand side looks like MCAT to me. MC delta T looks like MCAT. So ever since I was a tutor way back in the day, I would always talk to the people I was tutoring and say, you get a lot of heat for taking the MCAT from your family. They talk to you about it all the time, constantly. So if you want to remember this equation, the heat of the system is related to MCAT, which is the mass times specific heat capacity times the change in temperature. So let's take a look at the specific heat capacity. What are the units of specific heat capacity? They're very unique. It will be joules. This is an energy terminology, an energy term here. Joules, we know that. We've seen that before. So if energy is equal to Q, that means that Q has to be in terms of joules. If the specific heat has joules in the numerator, it must have a mass and a Kelvin in the denominator. When we plug this into this equation, these units, the masses would cancel, the kelvins would cancel, and we'd be left with joules. So the specific heat capacity will have units of joules per gram Kelvin. Now remember, this has to be in Kelvin. If you use Celsius, it's going to come out with a wildly incorrect answer. And the grams have to be in grams, not kilograms. It has to be in grams. What that means is our masses, we're going to have to convert to the correct units. We're going to have to convert the temperature to the correct units as well. So this is called the specific heat capacity. Specific heat capacity. This is the amount of heat required to raise 1 gram of the substance being looked at by a Kelvin, by 1 Kelvin. So that's what the specific heat capacity is. Every substance has a certain amount of heat required to raise 1 gram of it by 1 Kelvin. So this is the specific heat, we also have a thing called the molar heat capacity. That's written with a capital C. And the only difference between the specific heat capacity and the molar heat capacity in the units is the grams are now replaced by a mole. Everything else remains the same. So we have molar heat capacity. And that makes sense. We have a new term. We've changed our unit from grams to moles. We know how to do that just off the cuff. We can look at the periodic table and use our molar masses to go from grams to moles. So we can directly convert from specific heat capacities to molar heat capacities. That does change our equation a little bit if we're dealing with our molar heat capacity. This is equivalent to saying the moles, N, times the molar heat capacity times delta T. So we have these two different equations. This is the one that we normally use, Q equals MC delta T, but we can change and use the molar heat capacity by changing the equation to N times molar heat capacity times delta T. So these are the two equations that we're going to be working with tomorrow. Really, it's just a plug and chug. You'll be given masses, you'll be given temperature differences, you'll generally be given the specific heat capacities, and then you can calculate the amount of heat absorbed or given off by this system. So we'll work on a lot of problems like this tomorrow. I just want to break down the equation and hopefully give you guys a better understanding of what the specific heat capacity is. It's a constant, and it's constant for the species being looked at. And then we have a molar heat capacity. This is also a constant, but it's a constant that changes with the substance that we're looking at. So we'll do a lot of problems tomorrow, but that's all I want to show you about the heat equation.